Class. Okay, so please welcome
All right.
Nathan, or Nate.
All right. So we're going to do a impromptu talk here about some of the stuff I've been working on with the language and the parser. And this is stuff that will be in the next purescript release, which is 0.13, which will hopefully be soon. But my name's Nathan, or Nate Faubion. I'm a developer at Wake Security, and we are hiring a PureScript UI developer. If anyone is interested in come talk to me. But all right, so let's get started. So I took on the task earlier this year of kind of reworking the parsing internals for the language, and we had a few things that primarily we wanted a good format, and due to just kind of the language kind of organically grew, and like the data types around it and the parser all kind of organically grew as the language grew, and so there were a number of roadblocks to implementing like an actual format of the language. And Hardy Jones has a project called Purdy, and he's done an admirable job doing the best he can with what the language provides, but like there's still just a lot of cases that you just can't handle just because of the way the parser works. The parser, some of the issues with like the old parser were that it does a lot of desugaring in the parser, so that you don't know necessarily how someone wrote something. So if you have like a multi-arg function or argument function, it will it'll just parse it as like a curried function. And so you don't know if they wrote it that way, or so you have to make just choices for the user regardless of how they wrote it. And so the main thing we wanted was the ability to precisely describe how the person wrote the syntax. And so I started a project called purescript-cst, which is a concrete syntax tree. And the point of this is to specify an exact specification of the language syntactically versus just like abstractly. So every bit of syntax that a user writes is represented in this tree. And one of the nice things about it is that you get a kind of like a nice print and parse as ID. So if you print whatever you parse, you get exactly what you originally parsed or what the user originally wrote. And so, and there's a number. Well, this is the main module, like just the types, and this is the full specification of the language in Haskell data types. And so what we do, it starts with just like some boilerplate. Like this includes everything from like tokens to white space to comments, everything in it. And so this is all the tokens of the language, and all the tokens are annotated with their it's called the data type is called comment, but it represents how many spaces or prefix the comment, or any lines that prefix the comment, and then any comments themselves, like actual text comments. And so every token is annotated with that. And then every production in the tree, so if we go here to like a type or a kind, every token is represented in the tree. So it is represented in left to right order, so you can always get exactly, you can go from a string to getting a stream of tokens, to building up a tree, and then going all the way back again, and get the stream of tokens back, and then get the original string back. And so this is great because we always have an exact representation of what a user wrote, and if we want to format it, we can always take into consideration what the user wrote when we go to format something. But there's also a lot of cool, hopefully, it's my hope that we'll get a lot of sort of syntactic refactoring tools out of this, because you always have what the user wrote, then you can do any sort of like project-wide refactorings or rewritings and still get, only touch the things that need to be modified versus like reformatting the whole module. Question?
Is this going to be a standalone library? Is it created?
Well, I started it as a library just to like iterate, but it's actually in the compiler. It's merged into the compiler, and like the old parser doesn't exist anymore. So this is all like, this is the language now. Like the syntactic language is these data types. And what we actually, I preserved the old AST. It's a lot of work to rework it. And there's actually some semantic passes that are done on the original AST that are not written for the, that are not, I didn't rewrite them for the CST. And so, but my hope is that we can kind of gradually migrate those semantic passes over. So like things like sections and operator desugaring, those are all done after parsing. And it basically reparses the tree based upon new information that it gets after it parses the whole module structure, the whole module dependency tree. And but my hope is that in the future we can kind of like prune down the core AST and it can just be like a type checking AST and like for type checking and elaboration. But so this is, it's just all, I wanted it all in a single module so that like for like the data types at least, so you can always just have exactly like the language is here. Like you look at it and this is the language. And you know, it has a lot of deriving. This module takes a very, very, very long time to compile. But I think it's about, you know, it's less than 500 lines, so you know, it's not too bad. The language itself is, when you're like actually getting to start writing the parser, it starts to feel like, oh wow, this is a lot bigger than I thought it was. But then you look in retrospective and compared to other languages, it's not actually that big. But otherwise, there's not really a whole lot interesting about this specifically. But it's just an exact representation of what purescript is syntactically. And so the next decision that I originally just mapped all these out as best I could. And the next decision was actually how to parse this, how to how to build this tree from a string. And the main consideration that I wanted was I wanted something that could be used to actually serve as a specification for the language, and how, like what the actual grammar of the language is. And one of the problems with parser generators is that, or parser combinators, is that you end up mixing a lot of like state logic in with your parsing, and it kind of fixes your parsing strategy to whatever the parser combinators tend to, they tend to be very greedy. And so there's actually a lot of edge cases in the old parser that you didn't even know could parse but do. And it's just due to like greedy nature of parser combinators. And so there was a lot of weirdness to kind of like tease out. And so consequently, there's a lot of little breaking changes. In reality, there's not that many. Like I think we have about 60,000 lines of code, of purescript code, and I think we had about 4 changes, you know, overall. So the breakage is pretty minimal. And I think Lumi had maybe 10. But we just cleaned up all those edge cases, and so the goal was to have something more declarative that can be served as a specification for the language. And so in an indentation-sensitive language like purescript, you have to deal like, how do you specify the indentation rules of the language, and it's kind of like an implementation detail almost. Like the grammar of the language doesn't really care about indentation. Like as long as you have some way to represent like a token for indentation, you can put that into the grammar. But it's then how do you actually get that into like the token stream? Like how do you actually like produce something that it can match on? And so it works in, it starts in like a lexer phase. And this is where we get the main tokens. And this is all just a handwritten parser. The other one, the old one was, like a parsec one, and it was, it served its purpose, but it was pretty slow, like overall. So this one's actually handwritten now, and I think it's about 7 to 8 times faster than the old one. But one thing that's nice about this is that it works as a lazy stream. Like the whole lexing procedure works as a lazy stream. And so you only lex as far as you parse, and it all like works in lockstep due to laziness. Like the lexing and then like the layout insertion and the parsing all works in lockstep lazily, so that you can do things like lazily parse just the module header, and that's all you consume, then it doesn't actually parse any more of the module. It doesn't even lex any more of the module. And so, yes, this is all pain. It's kind of gnarly, but it's not too bad. I think the gnarliest part is like comments. So like because we distinguish like what is a leading comment versus a trailing comment, you have to like do all this like logic to like break comments up to figure out where they go around a token. And the reason why you want to do that is so that if someone writes like a trailing token and then a comment after it, you want to preserve that it was still attached to that token on that line, but that's now a trailing token, like a trailing comment versus a leading comment. And I think the old one just always only listed everything as leading comments. So if you wrote something after it, it would be attached as a leading comment to the next token on the next line, but that's not actually what the user intended or meant when they wrote that. But there's not a whole lot interesting in here. In the lecture, the most interesting part is just what we removed from the language. So the old one, the old parser, the old lexer used basically what parsec provided as the Haskell grammar. So it was like, what are the rules for parsing PureScript is look at what Haskell does for their grammar, and that's our rules. And there's actually a lot of like stuff in Haskell that nobody uses anymore, and there's really no reason to support it or specify it. So we actually removed a lot of rules around like the lexer tokens. And so I think the biggest thing is like escape codes. Like Haskell supports an ungodly amount of escape codes and characters, just obscure stuff that nobody's ever used. So we basically removed everything except basic white space ones like return, new line, tab. I think we still support white space gaps. So like you can have like a backslash and then arbitrary white space and another backslash, and it just eliminates that gap. But otherwise, it's just hex codes for characters. And I've tried to like represent these all in comments for now. Like this could be written as an Alex parser, but this took me a day to write, and like in that time, the time it took me to learn how to use Alex, I finished this. So you know, it was so. But I've tried to at least like specify the regular expression rules for all these. But yeah, so like numeric, something we added was that numeric literals now allow like underscores. So like Rust, you can write numeric literals like this. But otherwise, we removed for like strings, we removed like numeric escapes. We removed so basically all that you have in strings are the basic ones that everyone uses, and then hex escapes. So you do /x, and then you get like 6 digits to escape a character. But otherwise, all the numeric rules aside from underscores are the same. There's no like binary or octal notation though. We might add binary back, but I wasn't able to find any usages of octal anywhere. And I don't think most people know that octal even exists in the language. But the lexer otherwise isn't. It's just a handwritten lexer, so that's not the interesting part. But what is pretty interesting is specifying how like the indentation rules work. So the thing in Haskell has an algorithm called it's the layout algorithm, and this is how Haskell inserts tokens for layout context. So in Haskell, when you write do and foo bar, this actually inserts invisible tokens like this, so that when it goes to parse it, it has like explicit delimiters everywhere. Like to the parser, these are explicit delimiters, but the user never wrote them. But the layout insertion algorithm infers these based upon what you wrote and what the indentation is. And so we have something similar to that, but the problem that Haskell gets into is that there's an odd condition called the parser error side condition. So like it looks really clean, and then it gets to this one point where like, oh, well, if you get a parser error, then you should back up, try to insert a token and see if it keeps parsing. And this is something that kind of, it's a little weird just because something you can't replicate. It's an implementation specific thing for how especially happy parsers work. that you can even do this in the way that it's specified. And so I wanted to try to specify a purely lexical algorithm for representing layout in PureScript, and that's nice because it doesn't require any parser implementation details. It's a pure pass over just a token stream. There's no like state involved. There's some basic like stack state, but otherwise nothing. It just matches one token at a time with a delimiter context, like a delimiter stack, and using that, it's a pure pass over it. So in this sense, like the layout, the indentation rules of PureScript are completely separated from the parser. And this is just nice from a specification standpoint. But this is the algorithm that it does, and it's a delimiter parser, and so it's kind of like, okay, here we have an open paren, we're going to keep moving. You know, we put that on the stack. We got another like an array, like an open square. Put that on the stack, and then it makes sure they all match as like a basic delimiter parser. But the problem is that PureScript has a lot of sort of these implicit contexts that are like actually like keyword delimiters, like case and of. Like you have a case represents the head of a case, and then the of delimits that whatever was in the head. And then there's lots of like if then else. So you have if and then an expression, then an expression, and then else and an expression. So there's all these other like delimited contexts that it has to keep track of. And in some ways this makes it, there's actually a lot of like edge cases too in like the PureScript language that are a little tricky to handle, and what actually makes this more complicated than you would think. But I try to write this in a straightforward way where it's just matching on a single token and all the rules are defined on that token. Like it doesn't try to, so in some cases it's actually more verbose than it needs to be, but I tried to make it as straightforward of once you hit this token, you apply this rule or these rules, and so there's some duplication in that case. But that's basically all it does is it goes through, it hits a token, sees if it's one of the delimiter contexts, and checks the indentation if it needs to, then it will like collapse it and insert like all the explicit tokens as necessary. And so what that means is, if you look at like a test, let's do, so one of the more complicated ones, let's do case. There's a lot of like weird stuff with case, the way case works. And so these are like, I have golden tests for all of these. And so you might write something like this, and most of these like you would never actually write explicitly, but they expose like certain weird edge cases around how commas work, and like whether you have an expression. So most people they might write something like this. You know, and then you have your patterns here, and your expressions here, and then you have like a prefix comma. But the actual grammar of the language doesn't, like the original layout algorithm I wrote was, like 20 lines long, but of course, and it parsed most things, but of course, the devil is in the details of like, what does your grammar actually allow versus, like what do people write versus what it actually allows. And so this can actually then be written as this, or this, all in one line, something like that. And so dealing with where you insert these, it gets complicated very fast, especially around commas. And so I have like layout tests of all these weird edge cases. Like you can't even see what this parses, but you can't visually parse it as a human, but it's something that the grammar has to handle, or like the layout rules have to handle, because that's something that makes sense within the context of the language. And so we make sure that we have golden tests to make sure to see where all the layout rules are inserted in there. And so like you wouldn't even have caught that like on your eye of like where these commas line up versus where it is in the array, or whether it's so you have commas in an array like right here, you have commas in a case head, you have commas in guards down here, and so you have to keep track of all those contexts to make sure that it's actually inserting layout rules in the correct place. And people don't write that, but the language allows it. And so I think I did probably 5 iterations of this, just like uncovering more and more edge cases in like how the PureScript language works. And so layout or indentation sensitivity is I do not recommend, like if you're implementing a language, Don't duplicate Haskell's indentation rules. They are incredibly difficult to get right.
Can I use failure rates as semicolons?
No, you cannot. No, this is just for, so they are tokens, and so the pretty printer, like the token printer, like it will print them, but no, it will not parse them. So no, there are no, it's still indentation only.
Is there a reason not to run it, or?
Yes, and it is, so it's similar to the JavaScript rule around record literals and blocks. And so if you allow this is an ambiguous parse. And so this is either a do block, an explicit do block with a foo expression, or this is like do with a record and a label one. And so in JavaScript you have to add the parens explicitly, but there's a few cases like that. So no, there are no. I thought about adding them to cases because it's not as bad, but like especially around like do, it's pretty hard to reconcile those, or at least not without like introducing those sorts of like you have to use parens or something. But so yeah, that hopefully this can. It's probably more complicated than it needs to be. I haven't gone through, like I said, I did about 5 passes of this algorithm, and but at the end I got something that I was really happy with, and I was just like, I'm done with this. You know? And so there's probably a few cases where it can be simplified, but there's also some like tricky stuff, like a, do, in, is actually pretty tricky because of because let and in is an expression, but then there's also a, do, and in, and the layout rules around that, and how the keyword in works to delimit those is kind of tricky. Probably the most code was added to this to handle unquoted keys. So you can do something like foo.where or foo.do as record labels, and they're unquoted. The problem is that these are layout keywords. And so naively, the algorithm will see like this do token, and it will start to insert like implicit layout. But if it's a record label, you don't want to do that because you'll end up with like a weird parse. So instead of, if you do foo.do bar like that, and this is applying bar to the do function within the foo record, you know, naively it would go in and do like the same thing as before, and it would insert these other tokens. And so where it was function application is now it thinks it's like a do keyword. And so you have to like mask all these states within records and labels to say like, okay, not in this, like if you're in a curly brace context, we have to know that you can have these keywords and they don't apply to layout. And then also if there's like a period, but then also a period is used in for all definitions, so you have to mask the for all to like, so there's all these like rules that end up overlapping. And like if I were like specifying the language, I would say like, okay, so layout keywords have to be quoted, and that solves that problem. But we've already allowed that, and so a lot of the rules, or a lot of the tricky rules, are just due to what we've already allowed in the grammar, and it was easy. It's easy to implement with parser combinators because you just keep going, and then if you don't get it, you just backtrack and you just keep going. And if anyone has written like large like DSLs, like HTML type DSLs, where you have large expressions, if you get one thing wrong in like an array, like an extra comma, like the error would be like at the root of your program. Like I've had errors, like parse errors, span hundreds and hundreds of lines of code that I've had to like binary search, with like comment out code to figure out where this parse error is, just because like due to the way it's so easy to backtrack with parser combinators and get yourself into a really weird state. And that's something really interesting about parser combinators, is that you're always kind of like, how do you separate the desire to write a modular production rule, where like I can just call this production rule on itself, versus I can have an efficient parser with good errors. And so if you want to modularize all your production rules, you end up having to backtrack farther than you would like to, and so your errors suffer due to modularity. But so what I did was I used Happy, and Happy is what GHC uses, and Happy is a parser generator. So it's a DSL for your grammar, and it co-generates for you. It co-generates an efficient parser. And Happy specifically is a parsing strategy called LALR1. And the good thing about that is that it uses one token of look ahead only, and it never backtracks. And so errors within the grammar are always precise to the exact token that it fails. You never get into a state to where, okay, I'm going to speculatively try something, and then I might have to try something else, and then I'll have all these error states, and I have to like pick one and try to decide. That's where you get to like ambiguity in grammar. Is like, okay, I got all these cases that might apply, and so I have to speculatively try and parse all these different states, and then figure out maybe which one the user intended. And there's actually some cases where that's impossible to avoid in the purescript. So I'll talk about in the purescript grammar. So I'll talk about some of those. But these are just like utilities, and so in some cases we do use combinators. So like in the PSCI in the REPL, it has kind of like this ad hoc grammar of like we're going to combine just like import rules, and we're going to combine expression rules and a few declaration rules. And so I export Happy supports partial parsers, and so you can export specific productions, and that only parse until they fully reduce. And so a lot of it's boilerplate. Like this just tells you what the tokens are and how to actually match on those tokens in the stream. And there's some boilerplate utilities, and again some like boilerplate kind of conversion things. So like an identifier, we convert that to a specific data type. And it gets more interesting around there's like logos. And so here you get into the actual syntax of the language. Here's like kinds, which is super simple. Types is pretty simple, but types there's a weird ambiguity in the type grammar of rows versus kinded types. And so if you have a type in purescript you have to ask, or even this right here, we'll do this. Is this a row, or is this the type variable A, and we've just annotated it with a kind? And so this is somewhat ambiguous. So it's kind of similar to the JavaScript rule I talked about, like the records. And that if you want to actually kind annotate something that looks like a label, you have to wrap it in parens and to annotate it. And that's how you like distinguish the two. And that's done by having like a totally separate like productions for kinded atoms. And so there's some duplication there, but it's not too bad. Like the type language is pretty simple. Some other trickier cases are, so we have a really tricky, so how we do record updates is really, really tricky. So in Haskell, you have record syntax where you have something like that. And then to update it, and that's to construct it. You use the constructor. And so if you did like that, and then you could update that by assigning it like here. And so the expression, it sees these braces like in the Haskell grammar. Like this isn't ambiguous in any way, but in purescript it's a problem because records are like there's no tag for a record. So they just exist on themselves, and so the record update syntax is the same in purescript. It uses this equal sign, but it would be something, use this to construct it. And then in order to know that this was a record update versus, so like here I would pass this record literal to the function A. The only way to distinguish these two is to look all the way ahead until you get to an equal sign. And then now you know I'm parsing a record update. And then I have to go back. And the thing is, this actually has different precedence than application. So this expression in purescript, just like looking at it, you think, okay, this is a foo with two arguments, like the foo function, and you have argument A, and then you have this other record thing. But because it's an equal, this is actually, it has different precedence rules. And so this is actually applied to A as a record update, which is then foo with only one function. And so, because it looks like application, and it has a totally separate precedence. It has a tighter precedence than application. You have these cases where you have to go into like and parse this, and then you have to check, you have to speculatively parse, because I only have one token of look ahead. I have to parse, maybe it's a record literal, or maybe it's a record update. And then once I have enough information, I can reduce that. But then I have to go back and change the actual associativity of it in a different rule, in a lower rule, to reassociate it to whatever application was, in case it was application. So there's a lot of like tricky cases in the purscript grammar to handle around that. And there's also, we put in some ad hoc rules to parse some like weird edge cases that lots of core libraries use for case, but that's not super important. But otherwise, the whole language is now in just a single module. And some of the tricky cases that use backtracking is that, or that require, another case that uses unbounded look ahead is when you have like a binder like this and then some expression. You might have like pure A or whatever. Is that the rule is that a do statement can either be an expression or it can be an expression prefixed by a binder. And you don't know which one you're going to parse until you see the arrow, back arrow. But that requires unbounded look ahead because a binder can be arbitrary in size. You know, it might have 20 arguments. So the way Haskell resolves this is that Haskell parser basically parses everything as an expression because almost everything overlaps with expression syntax in some way. And so the expression syntax in Haskell is really like a proto-expression syntax. And it's more permissive than what Haskell allows for expressions, but it's like a superset of expressions and binders and all those sorts of things. And so it actually parses everything as an expression. And then it has this kind of ad hoc function that goes through and reparses and reassociates all those like things and binders. And
Sorry, I have a question.
Okay, well let me finish this real quick. And it reparses those and then like splits them apart and then. But that's how I originally wrote it. But it's really hard to audit and actually it's really hard to make sure that it actually satisfies some specifications. So in order to get around that, I introduced some backtracking using some kind of like happy hacks. But you had a question?
I was just wondering, so what you wrote on the other one, or generally, how is recursion handled? Because, so what you just wrote on the previous the scratch pad or whatever, it's like this do statement is an expression, and then you use, the right side of that arrow, the same expression. But because, like, I'm assuming it works, but like, I can't, that sounds hard.
That's just something that Happy does. Like, you don't have to worry about that. You can write fully recursive production rules. And the thing about LALR parsers is that it's what's called bottom-up parsing versus something like parser combinators, which is top-down parsing, which is generally how we think of parsers. Like if we're going to handwrite a parser, we're going to think, okay, I'm going to look at this token, and that's an if, then I'm going to start parsing if ones, and then I'm going to parse an expression. And you're starting at the top of your rules, and then as you hit something, you'll go down into it. And that's where if that fails, then you have to figure out how to backtrack. And what bottom-up parsers like Happy do is that they maintain like an intermediate parse tree, and they don't actually start reducing anything until you get to like the leaves of the tree. And so it's called like a shift-reduce parser. And so there's two primitive operations where I shift a new token on off the stream that I'm going to look at, and then once you have enough information, and based upon the state that it's in and that token and the look ahead, it's going to then start applying the reduction rules for your language. And so it actually starts evaluating your code, which is like these like terminals here, where you actually build your AST. Or in like the monadic rules, you can run like arbitrary monadic code. But all the stuff at your leaves is evaluated first, and then it works its way back up, and then it evaluates everything like the larger expressions. And so you use what's called left recursion. And so in grammars, how it's recursive, it actually matters, whether you have like a recursive prefix or you have some known prefix and then a recursive tail. And so in bottom-up parsers, you use left recursion. And that actually kind of you just have to like write it in a certain way. So first, either case you have to write in a certain way, and in a lot of ways that purscript is a lot nicer, but I'm not going to go into that right now. But so I had to introduce some like ad hoc backtracking, and I use the partial happy parsers, and because you know it's always one token of look ahead, you always take the look ahead token and put it back on the string, and you can run your backtrack. And so that's what it does for do statements. It does some basic backtracking. And this is usually bounded. And like the actual cost of parsing a general expression and going through and reassociating the tree and pulling out like a binder is essentially the same cost of what it would be to just do the backtracking. And because it's just like a known production, like the errors they're not terrible. They don't go crazy. It's delimited pretty well. But yeah, so this is, my hope is that this will serve as like the basis for a declarative specification for the purescript language. This is the entire language in this file. And so some cool things we did were, we can do partial parsing of modules now, I mentioned that. And so it can lazily, or it can parse and consume just the head of the module, like the module header, and then continue parsing the body and completely share that state. And it only parses, like everything is done lazily from, like it loads in the file strictly, so you have the full file in memory, but the actual parsing and lexing is done lazily as you consume it. So you can consume just the head of the module to resolve like the dependency hierarchy. And then you can just force the rest of the parse tree. And it will do all that work then. And so some other, there's like just a lot of boilerplate too. We have to convert it to the AST to do all the other stuff. And so there's just like tons of work for that. But it's all non-interesting. But some of the things we broke in this is that I think probably the biggest one, but it doesn't actually affect hardly anyone, is that the only white space allowed is ASCII space. Like in the actual, like when you're writing a sort, like you can have any space like in a string or something, you know, like, or a raw string, literally. But like to actually write the code, purescript code, it only allows ASCII space. And part of the reason we did that is because we only allow indentation. And Haskell, you can write Haskell as if it's explicitly delimited without white space, but so allowing like Unicode white space, non-breaking spaces, or zero width spaces make some kind of sense, I guess. Nobody would want to write that, and I would consider it a mistake. But since we have to determine like layout by column exactly, we just went ahead and made ASCII space the only white space allowed in the language. And that means that it's always, there's never ambiguity of like how many columns does a tab take up. Like in Haskell, I think a tab is 4 characters, but you have to arbitrarily pick that for layout. And that may not be how the person has decided to format tabs in the file. You know, it might have been 3, you know, but you don't know. And or things like zero width spaces, like does a zero width space take up a column? You know, like there's all sorts of like decisions around like how you handle ASCII white space or Unicode white space that just doesn't make sense in like the layout rules of a language like purescript. So we just made spaces the only white space. And we took out a lot of, like most of the breakage was around things that you wouldn't even write. Like most things, the vast majority, I think I only had a few modules like in like the package set that didn't parse. Because there were like edge cases, some of the really gnarly edge cases in purescript, like you could write something like module foo. You could write this, where like the qualification spans multiple lines, because the old lexer would lex each of these as separate tokens, and the new lexer lexes all qualifications as a single token, and so it won't allow white space in them. So you can't write weird stuff like this. You have to write it all on, you know, one line. And that applies for every, like you used to be able to write something like, and you know, have an operator in here, you know, and that was like the new lexer doesn't allow that. You have to write it all as like it's a single lexing. So that's some cases where we broke things. But there are things you wouldn't write anyway. So a lot of things around layout, there's a lot of like weird cases in the old parser, especially around cases, or weird cases, yes. But like an old thing, or something that it would allow in the old parser, and this particular one it does still allow. But if it's just one case, it does allow this. But this is something that kind of violates the layout, the layout rules. And that the layout rules are like, when you have a layout keyword like of, it looks at the next token, F on food, or food, marks that as the layout column, and then everything within the case then has to be aligned to that layout column. So it would have to be over there. And if you kind of move this back here, then it should insert, because it's indent or dedented, it inserts a closing opener. But so that's there's a lot of weird cases around that in the old parser that we don't allow anymore. And I think some of the biggest ones were you could write something like this. And this doesn't really make any sense, and it parses it correctly, but it doesn't make any sense for layout rules, and that's just because this A expression doesn't happen to fall exactly on this column. So there's some issues with the old offset rule for inserting layout. And so and I think some that we actually wrote in the wild were the old parser. In some cases, if you were in a do block, you could write. In some cases, you could do this, or I think it was if there was a lambda. So if you did this, you could write this. And this doesn't actually, for how like let layout works, this doesn't make sense because the layout starts at this token, so this has to be indented past that. But there's some edge cases around how lambdas work, and the greediness of parsing a lambda, it allows that. And so it kind of like jumps over the offside rule. And so I think we had a case like this. This was one of our 4 cases. One of the cases was we had an identifier called for all. So we had a declaration for all, like this, And so we disallow for all everywhere. That's now a reserved keyword. So that identifier rules for types and identifier rules for expression are the same. I think one of the weirdest cases around the old indentation rules was that it allowed something like, you could write this. So this is a valid, with the old parser, this is a valid single expression. And the way this parses is it actually parses it as, but even though you've inserted a new line, and even though the indentation falls back, because it's greedily parsing an expression on the right-hand side of this bind, and because this expression doesn't happen to fall exactly on this column, it doesn't insert a separator. And so you have this totally bizarre rule here. And so that's something that we fixed. I think one of the breaking ones was, I think this was in signals. There's an issue with guards. And so if you have this, and say you have, okay, so you have multiple guards, so we do, I'll just do ellipsis. And say this is actually indented like this. And then you do, pure, whatever, true. And then you insert another guard. Like that. And so the old parser accepted this, but the new parser requires this to be indented. I think at least to the guard, like that, or to there, or something like that. And so that was one case that broke in signals. There's like a weird case where I think some code was added, but then wasn't reindented. So, but I think that's most of the breaking changes. Like we removed, all the escape codes and some of the numeric literals, and then we added a few things. But I think that's about it. But it's a lot faster. So the big thing about this parser is that it's a lot faster. I think on average, is about 6 to 7 times faster than the old parser. A lot of that is due to the lexer, because the lexer is so significantly faster, but I think the parser itself is probably at least twice as fast, probably 2 to 3 times as fast. And the errors are a lot better as far as like locality, because it's like a parser generator, and because of the, you don't always know like, oh, like I was in an if block when I tried to parse this, and so some of those rules are kind of missing. Like, oh, no, this should be an else, you know. Some of those kinds of things are missing, but the errors are actually precise now for like their location. So we might add, like, there's some ways we can add a lot of that back, but it's kind of a manual process of adding special cases back. So, like, some of the special cases I added were around, like, if you type a record literal with an equal, and it's actually a record literal, it'll tell you, you know, that this is supposed to be, like, you know, I saw an equal, but this is a record literal, and it should be a colon. So there's some cases like that that already handles. But I think in the future, I would like to see if I could report multiple parses. I had done multiple parse errors. That is, it could parse up to a point, and then if it hits an error, it can you know, lop off a chunk of the stream and continue parsing again. And I had done some work on that, and it worked all right, but sometimes it reported more errors than were necessary. So there was some finesse, and I didn't want to like get into it. But I used the layout delimiter context to figure out, you know, I can consume tokens up until the next like layout section ends, and then keep parsing again. That's something we might add there. But yeah, so that's about it, I think. But my hope, yeah, is for this to serve as a way to specify the purescript language and open up a whole host of tools to use for purescript language, like syntactic tools. And that was something that was really frustrating with the old parser, is that there's no way to have like syntactic tooling around the purescript language. It's just, you just kind of like hacking things in, like the way the like PSC IDE works, which is kind of like, it's pretty, even though it's only like messing with imports, it's still pretty rough. The old parser, how do you do that? Yeah.
Have you tried doing any like prescriptive stuff, like inserting stuff?
So the only pretty printer that exists in the compiler is just the token printer, and I use that for the golden tests. And that just works on the token stream. And so that at least works, but Hardy Jones has already, I think he's already updated Purdy for the new, his goal was to have Purdy updated for the new compiler release.
So do you push, like, when you annotate the CST with the original information, do you push that down into the AST as well?
Mm-hmm. Yeah, so all the, what the conversion module does, it derives, so the original, the CST doesn't actually like tell you any location information. It just has all the annotations of like the indentation and then like any comments. And there's rules to derive positions from that. And so if you ask like what the position or what the source position is in this tree, it just like it calculates it dynamically. And in this conversion function, it goes through and resolves all those for the module. And does all the original annotations. This actually fixes a lot of issues with the old like position information. So originally the lexer would like annotate the source position of a token. It was the start of the token, then all the way up until the start of the next token. And that would include any sort of comments in between. So you know, your original identifier may have been 5 characters, but because you had new lines and comments, it would then, the position range would include all those new lines and comments as well. And so that's something that was resolved here. There's also a weird edge case where if it was the last token in the stream, because there's no next token to check, the original, the span was like 0 span. And so like something like that stuff is fixed. And so I can take out, so I have a bunch of hacks in, use purescript-cst, which like prints out the original code that you wrote for the error. Like there's a bunch of hacks in that to try to like reduce that error span. Like it gets this giant error span, and it loads up your original file and kind of like iterates backward until it like thinks that, okay, this is no longer a comment, this is no longer a comment, this, you know, stuff like that. And so I get to remove all those because they're all precise now. And so a lot of the error reporting itself is a lot better if you're just using like the ranges from the original compiler, just from the compiler. So something I hope we get out of this is migration tools, like migration tooling. Is because these are like in single modules, it's also easy to like vendor the parser because it's just, you know, it's all localized. And so as we iterate the grammar, we can vendor it pretty easily and then provide migration tools around that. And so I think something I might require for like future, like large, like or syntactic or breaking changes like that is that maybe if we get like a migration tool, we can require everyone who's going to like propose that to also propose the migration rules for it, so that we can always migrate code bases based on any breaking changes. But yeah, like the pretty printer, like I know a lot of us are really itching for a good pretty printer, and this should allow us to have a good pretty printer. And but yeah, I think like refactoring tools will be pretty good too. Will be nice to have if someone wants to like start on that. Like, but yeah. All right, that's it. Any other questions? Yeah, it's in the compiler repo now. Like it's already merged. So like this, hopefully we'll get like the .13 release out like within the next week or so. I mean, it was scheduled for this weekend, but I think there were some tickets we wanted to merge or to fix. But so hopefully like next week that'll be out. But yeah, this is already in master. The old parser is completely gone now. So this is all that exists. This is the language now.